Hi everyone, I'm Sangeetha Abdu Jyothi. Today I'll be presenting my paper on understanding the impact of a cosmic phenomenon that's capable of taking down the internet, which is solar superstorms. What are the impacts of losing internet connectivity? We know that it can affect our professional and social life significantly, especially now during the pandemic. For large businesses, the economic impact can be devastating. The revenue loss per hour for some of the large companies are estimated to be tens of millions of dollars. And at the scale of countries, it can be hundreds of millions per hour or in billions per day. And it's not just the economic impact. Many of the other critical infrastructure, such as healthcare, depend on the internet and will be severely affected during network outages. Now, what if we have an internet outage lasting weeks or months and spanning large areas across the globe? We know that the internet is a resilient distributed system which successfully withstood several natural disasters and man-made attacks in the past. So one might think that a large-scale, long-lasting global outage is never going to happen because it indeed never happened in the history of the modern internet, which interestingly is only 3 decades long. But unfortunately, this is a worst case scenario that could happen in our lifetime. The next once in a 100-year disaster after this pandemic could be a solar superstorm that's capable of taking down large parts of the internet. And today, network researchers and operators overlook this threat while building our infrastructure. In this talk, I'll present a deeper view of this natural disaster and its impact on various internet infrastructure components. There are 2 types of solar events that are popularly known as solar storms. They are solar flares and coronal mass ejections, and their impact on global infrastructure varies widely. Solar flares involve large amounts of emitted energy as electromagnetic radiation. So these are essentially flashes of light that reach the Earth in just 8 minutes. Fortunately, they affect only the upper layers of atmosphere and do not cause any damages to terrestrial infrastructure, but they do affect satellite communication. Coronal mass ejections involve emission of electrically charged solar matter and the accompanying magnetic field into space. And these CMEs can take anywhere from 13 hours to 5 days to reach the Earth based on their speed. And these CMEs are capable of causing significant damages to terrestrial infrastructure. So this paper focuses on CMEs, and we'll discuss their impact more closely soon. Another point to note is that both solar flares and CMEs often originate near sunspots, which are temporary dark spots on the sun caused by concentration of magnetic field flux on its surface. And so when the number of sunspots increases, there's a higher probability of CMEs occurring. How exactly do CMEs affect us? So the magnetized emissions are highly directional. And when the Earth is in the direct path of a CME, it interacts with the Earth's magnetic field and produces geomagnetically induced currents on the Earth's surface through electromagnetic induction. Fortunately, humans are protected from direct impact by the Earth's magnetic field and atmosphere. But this GIC can enter long cables and cause significant damages, particularly to long-distance internet cables, as well as long-distance power transmission lines. And cable repair, especially for submarine cables in the ocean, can be very expensive and time-consuming. Next, we'll see some characteristics of these induced currents to better understand the risk. Due to the orientation of the Earth's magnetic field, higher latitudes are at a significantly higher risk. And it's for the same reason that auroras are more closer to the poles. The induced currents also have a much higher chance of being induced in the higher latitudes. Now, since the impact is caused by interactions with the Earth's magnetic field, the induced currents can affect wide areas across the globe and are not restricted to the portion of the earth that's facing the sun. And GIC is only induced in cables, long cables with ground connections that are separated by large distances. So not all infrastructure components are equally vulnerable. And finally, conductors along different orientation on the Earth's surface are at equal risk. So in other words, north-south or east-west orientation of the cable does not matter. Now, the most important question is, when will a large event that affects the Earth happen next? So solar events are extremely hard to predict, just like earthquakes. And small-scale solar storms happen all the time. So what we are more interested in are solar superstorms that can have significant impact on our lives. The largest solar events on record have occurred in 1859 and 1921, which was long before the advent of modern technology. The 1859 event is popularly known as the Carrington event. And both these events triggered extensive power outages and caused significant damages to the communication network of the day, which was the telegraph network. And a Carrington scale event missed the Earth by just a week in 2012. The estimates for probability of occurrence of such extreme space weather that directly impact the Earth ranges from 1.6% to 12% per decade. But that's not all. The risk is not uniform across years because the solar activity goes through cycles. So here on the right side, we can see the variation in number of sunspots observed on the solar surface across years. And here we can see that the solar activity waxes and wanes in cycles with a period length of approximately 11 years. And during solar maxima, there is an increase in frequency of CMEs. And solar activity also goes through a longer term cycle of approximately 80 to 100 years called the Gleisberg cycle, which is in yellow and orange in these plots. So the peak solar activity varies significantly across this longer term cycle. And the frequency of CMEs can vary across solar maxima by a factor of 4. So here, an interesting thing to note is that modern technological advancement coincided with a period of weak solar activity in the past 3 decades. And now we are at the beginning of solar cycle 25, and the sun is expected to become more active in the near future. And due to the absence of extreme activity in the recent past, we have overlooked the impact of these events on our internet infrastructure. So the bottom line here is that a large event could happen soon, and the impact is significant enough that we should prepare our infrastructure for it. Now, how will our various internet components be affected? Localized infrastructure such as data centers can be protected from voltage surges caused by CMEs using transient voltage surge suppressors, which are relatively inexpensive. So they are mostly safe. Long distance cables constitute the most vulnerable components in the internet infrastructure. So today, long distance land and submarine cables carry signals in optical fibers. And the fiber itself is immune to induced currents because it carries light and not electric current. But these cables also have repeaters at 50 to 150 kilometer intervals, which are connected in series and powered by a conductor that runs along the length of the cable. And this conductor is susceptible to induced currents. So during a GIC, the cables could be damaged and we could have partitioning across in the global scale. Internet routers can be protected from direct voltage surges using voltage suppressors, so they are safe. Satellites are directly exposed to solar storms, so they generally have radiation shielding for protection from high energy electrons, but very strong storms can cause electrons to penetrate deeper into the interior regions of the satellite and damage its electronic components. Solar storms can also cause drag on satellites, which can lead to satellites losing their orbit and re-entering the atmosphere and burning up. Cell towers are protected from direct exposure by the atmosphere. Similarly, personal devices such as laptops and mobile phones are also safe. So to summarize, long-distance cables and satellites are the most vulnerable components of the internet infrastructure. All components could suffer from power outages, but they're not susceptible to direct damages. So to better understand the impact at a global scale, I looked at a broad set of data sets comprising of various internet components. So the submarine cable map consists of submarine cables connecting various continents. The ITU cable map contains land cable information from across the globe collected from various regional entities. The intertubes dataset includes long-haul fiber cables in the US. And then I also looked at publicly available internet exchange point locations and DNS root server locations. And finally, router locations with autonomous system mapping obtained from KAIDA. So first we look at the distribution of infrastructure components across latitudes, because we know that higher latitudes are more vulnerable to induced currents, but particularly latitudes above 40-degree threshold. So we evaluate the distribution of infrastructure components in this range. So here we have the probability density function across various latitudes plotted on the x-axis. And we look at the distribution of population and submarine cable endpoints. And we see that the population is more concentrated on lower latitudes, while the infrastructure distribution is concentrated on higher latitudes, especially in the northern hemisphere. And this pattern repeats across other infrastructure components as well. So in this plot, we look at the distribution of various components, other components. So on the x-axis, we have a latitude threshold. And on the y-axis, we have the concentration, the percentage of infrastructure components above that threshold. So the most vulnerable region is above the 40-degree threshold. Here we see that only about 16% of the world's population is in the vulnerable region, but about 35 to 45% of the infrastructure components is in this region. And this holds true for other components as well, which you can see in the paper. So basically, internet infrastructure components are concentrated in more vulnerable regions. Next, we look at the cable length distribution. So only cables that are longer than 150 kilometers need repeaters and need that conductor along the length of the cable, which is vulnerable to damage. So here we compare the length distribution of land cables with submarine cables. And we see that more than 70% of cables on land don't need repeaters. So they are not susceptible to damages during CMEs. But nearly 80% of submarine cables need repeaters and hence are susceptible to damages from induced currents. And these cables are also located in the ocean, so they are harder to repair as well. I also conducted repeater failure analysis based on latitude-based failure models, and there are several interesting observations. So the US faces a high risk of losing connectivity to Europe during a solar superstorm. So in the East Coast, most of the cables between the US and Europe are concentrated between the Northeast and UK, which is most likely for lower latency. And there are no connections from Florida to Southern Europe, which is the less vulnerable region if you consider the CME point of view. Fortunately, the cables between Brazil and Europe are less vulnerable. So it was surprising to find that the cable between Brazil and Southern Europe is shorter than all cables between US and Europe. And it's also located in the less vulnerable region closer to the equator. In Asia, Singapore has a very high chance of retaining connectivity to neighboring countries, even under severe storm. And that's because the cables are much shorter in this region, and they're also located in lower latitudes that are less vulnerable. So Asia has a higher chance of retaining connectivity. I also looked at other internet infrastructure components. So hyperscale data centers are concentrated in vulnerable regions. So while data centers don't suffer direct damages, access to these data centers can be affected when submarine cables fail. DNS root servers are highly distributed, and hence they'll remain reachable even under high network partitioning caused by submarine cable failures. However, location data on top-level domain servers and other authoritative servers was not available, and they were not analyzed. So we don't know the end-to-end picture. And when we analyze autonomous systems, we see that a large fraction of ASs have a presence in vulnerable regions, but the vast majority of them have a very small spread. So these are some of the observations. Now, a lot of questions remain open. So this paper primarily looked at internet partitioning based on submarine cables mostly. So understanding the impact on end-to-end behavior of applications remain an open challenge. So this will need to take into account both land and submarine cables, as well as the impact on other internet subsystems such as DNS and the interdomain routing protocol. Next, we need to devise solutions for improving long-term resilience of the infrastructure. For example, this could involve adding new cables in locations that are less vulnerable and other infrastructure expansion solutions. Another interesting direction is design of new interdomain routing protocols that will improve the path diversity in the wide area network during solar superstorms. Next, a useful feature of these storms is that it will reach the Earth only after 13 hours to 5 days after it originates at the sun. So this gives us a short interval to prepare our infrastructure for impact. So there are many interesting questions related to how can we use this lead time effectively to minimize damage. And more broadly, we also need to rethink our models of failure analysis. So current best practices on fault tolerance and resilience evaluation in software systems mostly rely on failure models that consider a limited number of failures. So to study the impact of CMEs, we need to test our systems under large-scale failures at a global scale. Another interesting direction is how do we reconnect a partitioned internet? So after a solar superstorm, the internet may be partitioned mainly due to failures in long distance cables, and repair of these cables can be very expensive and time consuming. So we need to be prepared with alternative solutions that can provide temporary connectivity after an impact. So examples could be internet connected balloons or high altitude platform stations or HABs, which are mobile and typically deployed in the stratosphere at heights of about 20 kilometers. So ideally, they should rely on renewable power sources such as solar energy, so that they can function even without any dependency on the power grid, and this can guarantee connectivity even during power outages. So there are a lot of design challenges here. Finally, the internet and power grids are both designated as uniquely critical because all other critical sectors rely on them. And they're also interdependent on each other. And both are susceptible to failures due to solar superstorms. So we need to study the joint failure characteristics of this complex interdependent system to better understand their failure characteristics. So these are just a few of the open problems, and there are many more discussed in the paper. So with that, I leave you with more questions than answers related to resilience of our internet infrastructure. So there is a lot of work to be done in this space. If you're interested in working on this topic, I'm hiring PhD students. Please consider applying to UC Irvine. Thank you.